Today we're going to be talking about an SN1 reaction, which is a nucleophilic substitution, which is what the SN stands for. The 1 in SN1 means that the reaction proceeds step by step, so each step is separate from the other step, whereas in an SN2 reaction everything occurs at once. There are three things in an SN1 reaction: the nucleophile, which has to be good or weak; the substrate, which is usually hindered, and it's usually a tertiary carbon that's the substrate. If there is a tertiary carbon, it has to be an SN1 reaction. It's too hindered for an SN2 reaction to occur. Now, if it's a primary carbon or a methyl carbon, then an SN2 reaction will have to occur. And the last thing is a leaving group. The leaving group has to be good in SN1 and SN2 reactions. So let's say you have a halogen. Halogens are generally good leaving groups, but let's say you have a carbon attached to a OH, and if that OH leaves, it's going to become an OH minus, and that won't happen because it's more stable attached to the carbon. We're going to look at this reaction here, which is a carbon attached to three other carbons, so we know it's a tertiary carbon, and it's also attached to bromine, which is our leaving group. So our first step of our general two-step process is that the leaving group first has to leave. So we have this right here. Also, that's attached to the carbon, not the hydrogens. So what happens is here, the bromine leaves. So we have this double hooked arrow to indicate that both of the electrons are going with bromine. This differs from our free radical halogenation, where only one electron, which is signified by the single hooked arrow. Don't get these confused. Whenever you know you're moving two electrons over, it's double hooked. Whenever it's single hooked, it's one electron. So we're going to form what we have here, which is a bromine with a negative formal charge. And that's our first step, where the bromine leaves. And the second step is where, I should have indicated here that this carbon has a positive charge because it's only forming 3 bonds. And the only reason this happens is because there are these other carbons here to stabilize the charge. So the charge isn't actually on this carbon, it's stabilized within the molecule, I believe. And then this is going to be attacked by the nucleophile. So we have this carbon attached to 3 other carbons, and let's say our nucleophile in this case is a water, OH2. The reason I'm writing it like this is because OH2, the O is the nucleophilic atom in this case, and it's going to attack that carbon right there. And what we're going to have is this. Right here. And normally this would be our final product. Like, we had our 2 steps. We had the leaving group leave, and we had the nucleophile attack. However, you might notice that this oxygen right here has a positive formal charge. What this means is that this is not the final product. If you can deprotonate here, this would be a good time to deprotonate after the nucleophile has attacked. So if you ever notice that positive formal charge, deprotonate if possible. Here another nucleophilic molecule is going to attack the hydrogen on this substrate, and what this means with electron pushing arrows is we're going to push another lone pair onto this oxygen to give it a 0 formal charge. What that's going to do is bond this hydrogen to this oxygen. So this means that our final product is going to look something like this, which is our carbon attached to 3 other carbons. And since we have deprotonated, we're going to end up with an OH. And with that H3O plus, which took the hydrogen from this oxygen right here. This was the deprotonation step, and this is our final product. Also, this OH group right here is called an alcohol, which you might have learned already or will later learn. Thanks for watching.